stoichiometric defect. So what is stoichiometric defect? The crystal defect which does not change the molecular formula of the compound. They are called stoichiometric defect. Stoichiometric defect, we have found that if you go for non-ionic crystals, in that case we can have two types of defects. One is called vacancy defect and other one we call it interstitial defects. In case of vacancy defect, the density of the crystal decreases, and in case of the interstitial defects, the mass of the crystal increases. As a result, we find the density of the crystal increases. Now, when the same thing we apply for the ionic solids, we find that ionic solids or salts are electrically neutral. So, this imperfections or defects in the ionic solids are classified into two categories. One you call it Schottky defect, and the other one is called Frenkel defect. In Schottky defect, we have found that in order to maintain electrical neutrality, if a cation goes out of the crystal or is absent in the crystal, to maintain its electrical neutrality, automatically one anion also goes missing. Okay, so in that case, we find that in Schottky defect, you have vacancies created both at the cationic site and the anionic site. Okay, we call it cationic vacancy and anionic vacancies, and we find they are almost equal. In case of the monovalent ions, we find the number of the cationic vacancies and anionic vacancies are same. Now, what type of substances show Schottky defect? The salts in which the ions are having very high coordination number. High coordination number means what? That size should be very, very large. And that is, in that case, you find generally this type of Schottky defects are being found in alkali metal halide salts. Alkali metal halide salts like sodium chloride, potassium chloride. Okay, like. Now, when you go for the Frenkel defect, we find the Frenkel defect is generally shown where the coordination number of the ions are less. And one more, the sizes of the cation should be smaller than the sizes of the anion. So in this case, what happens? None of the ions, they leave the crystal lattice, but the smaller ions, so that is the smaller cations, it leaves its own site or place and goes to the interstitial site. That it gets displaced from its own original position and moves to the vacant space that is available within the other particles. So, in that way, this type of Frenkel defect is a combination of two types of defects. One is that is original place as it is absent, so we call it is a vacancy defect, and as it occupies the interstitial space, we call it to be interstitial defect. So, Frenkel defect consists of two defects: vacancy defect and interstitial defect. Clear? Now, this is commonly or collectively also known as dislocation defect. So, what are the substances or salts they show? We know that if you want to get smaller cations, you have to move from left to right along the periodic table. So the cations that you find in group 11 or group 12, like zinc, then copper, silver, all of them substances, cadmium, these are the substances they show the depot defect. Like example is silver chloride, silver bromide, silver iodide, zinc sulfide, they show. Okay. But very interestingly, we find silver bromide is such a salt which exhibits both the Schottky defect and Frankel defect. I told you this is important for your exam. What are the consequences of Schottky defect? Yes, because ions go missing, so obviously you'll find the weight of the crystal will go down. So Schottky defect leads to decrease in their density. It lowers the density of the crystal. Second, yes, because various places, empty places are there, vacancies are there, so the crystal become now little soft. So because of that, we can say that the thermodynamic stability of the crystal decreases, and due to the empty spaces, ions inside the crystal can move. So we can say the entropy of the crystal increases. When you go to the Frankel defect, as none of the ions they leave their lattice, so in that case, its density remain same. There is no change in the density. Okay, but only thing is that as one cation moves closer to the other cation, I told you this is only for your entrance. In that case, what happens? There, the crystals become polar and it develops a dielectric property. Similarly, here also, as the cationic vacancies are being created, the thermal stability of the crystal decreases, its entropy increases. Clear? So now I'll come to non-stoichiometric. Non-stoichiometric. I told you to go through your book. And any word or anything sentence in your book you don't understand, to ask me. I know that you did not study, you did not read, and you will not bother to ask me because I have. Non-stoichiometric. Okay. So let us know what is called non-stoichiometric compound. Compounds in which the number of positive and negative ions are not exactly in the ratio as indicated by their chemical formulae are called non-stoichiometric compounds. This is the simplest step. Now, for entrance exam, one more sentence. Non-stoichiometric compounds are also known as butterfly. Double. See, whatever my knowledge goes, and I know, I shall try to tell you, not only for your board exam, but also for your entrance. That from my part, I'll do my level best to help you for both them.
Done, sir.
So, composition. Defects which bring change in overall chemical composition of compounds are termed as non-stoichiometric. Okay. So now how can you bring it? Say in a classroom, you have 20 boys and 20 girls. Huh? So you want the number of girls should be less. So what will do? Say the number of boys should be less. So what will do? Suggest.
Increase the number of girls.
Okay, then second. Second, tell Suppose I
Reduce number of boys.
huh? Yes.
Reduce the number of boys.
Yes. Same way it is being done. Okay. So now we know in a salt, generally we find cations are made of metals. Most of the salts, except ammonium salts, most of the cations come from metals, and the anions come from the non-metals. Okay. So how can you classify the non-stoichiometric defect now? Okay. So we can write down that non-stoichiometric defect are of two types. Suggest me. See, we will not study chemistry like a an alien subject. We'll study chemistry just like telling stories or discussing with each one of us. We will not think that it is a very difficult subject we are going to study. If you go with this intention, you can never study any subject. We think that we are talking to each other. So I have written here non-stoichiometric defects are of two types. Just like you told me, you can either increase the number of girls or you can decrease the number of boys. So what should I write now here? And I told you, salt is made up of cations and anions. Mostly the cations are metals and anions are non-metals. So what are those? So right now, yeah, metal excess and second metal deficiency. Or we can write this one, same thing we can write, or non-metal excess, metal excess defect. Second one is metal deficiency defect, or we can say metal deficiency means what? Non-metal is more, so we can write now non-metal excess defect. Okay. Now see here, the crystals which are being formed by cations and anions. These cations and anions are not visible to us. So it is not that we can pick up. So you have picked up one by one and you have thrown it, or you have added some cations found. So that you cannot do it. Okay. So how to do? So so first I'll explain to you. Then only I. Okay. Say I have taken a crystal. You need not. Say I have this is a crystal of sodium chloride. You know these sodium chloride crystals are being made by what? Is the chloride is always at the lattice point. This must be true because size of the chloride is large. Here you have chloride because it is face centered. These are the back end. Okay. Chemistry is very easy. unless it don't get scared. And sodium are always at the octahedral bonds. So where do you have octahedral bonds now? At the middle of each edges. अभी तुम लोगों को सब मालूम है. Never get scared of any subject. Nothing is there. Science is being made very easy these days. You need not do. I'm showing you. See here. So at the 12 edges are there. At the center of each 12 edges. And one is there what? Deep in the middle. So see here. How many are there? Chloride. 8 into 1 8, all at the corners. And 6 into half, all of the faces. Numbers. Sodium. 12 into 1/4. And 1 is inside. So in this unit cell, 4 sodium ions are there, 4 chloride ions are there. Okay, now this is unit cell, so you cannot see. So, but you can make, if you wish, you can make sodium chloride crystal at home also. It's very easy. You make a saturated solution of salt in your house. Okay, and after that, you leave it open, let water evaporate. After 2-3 days, you will find big crystals of sodium chloride has formed. All right. So now let me rub it. Why did I write it? Just to show the number of the sodium ion and chloride ions are same. So this is a big crystal that you have made. Okay. You have made these big crystals. The size of the crystal that I have drawn here, you can make this big size of sodium chloride crystal also. Now suppose this crystal I have kept on a smooth plate and I cover it with a bell jar. I remove all the air from inside. Okay, and to that I add here sodium vapor. Okay, sodium vapor, obviously sodium is a metal. So at room temperature you will find no metal goes to the vapor state, including mercury, though it is liquid. So I have injected sodium vapor and I have kept it at room temperature. What will happen? Is it not the sodium, just like water droplets collect on the smooth surface or any surface? So what will you find here? The sodium also will collect. Sodium is a soft metal. So this type of sodium ion will settle on the surface of the metal. Okay. See, this much little bit thing you have learned in your class 11 periodic table. That ionization enthalpy of sodium is very low. So what will happen? Sodium is going to lose electron. Sodium is going to lose electron. So now what will happen? This is the way it will lose electron. on the surface. All right, remember, electron is an extremely tiny particle, and we know in crystal, within the crystal, so much of empty space is there. 26% empty space in crystal for FCC is no joke. Okay, so now I've shown you how it is going to happen. Now I graph. Let us go step by step. Is it? I'm doing an experiment in front of you, and you have to develop a wonderful vision that you can even see the electron atom, everything. So one fine morning you got up and you found you have developed a divine vision. Everything around you can see. Even the molecule, you can see how the nitrogen molecule is going around you, oxygen molecule, carbon dioxide, all the molecules you can see. Just see. You think it is like this. So now let us go inside this. So see here, this is Na plus, this is the original crystal. This. Okay, this is our original crystal. Now what has happened? Yeah, this some substances have come out from outside now. So this is the original layer and this is the extra layer. In extra layer, what did you find? In extra layer, you have found sodium is there. Sodium is there. So this is the electron of sodium and this is the electron of sodium I've shown you. So this is the surface. Okay. Now see. You compare this upper surface is just like your drawing room. Okay. So how do you keep your drawing room? Do you keep your drawing room like just like your study room? Huh? Keeping different places. You have books are there, your dresses are there, your sleeper is there. Huh? You keep it like this, your drawing room. Hmm? Hello. How do you maintain your drawing room? Or you just tell that my sir, I don't do anything. I only eat and sleep at home. My mother does everything. So how's your drawing room? Does it not look very neat and clean? Okay. Suppose one of the chair of the drawing room is broken. Do you allow your guest to come and sit and fall down? We do not immediately replace that chair with a better chair from inside house. So in that case, what will happen? Actually, it is a sodium chloride crystal. So the upper surface also supposed to contain sodium, but here we don't find any chloride. You know what will happen here? We find from there this one is chloride. Okay, maybe from here this chloride will move. Oh, sorry. Let me write chloride here. So this chloride has moved. When this chloride has moved, these places has become empty now. So in that case, you'll find the electron from the upper layer will diffuse and occupy those spaces. See here, if you count, now we'll find the number of sodium ion and chloride ions are not same. Sodium ion is more. That is one of the way to create metal excess defect. Okay, this is one of the way to create metal excess. Just like as one of the lady, she told me, in that case, she can bring some of her girlfriend from outside to lower the number of the boys. Okay, see here, the metal has become excess. So this type of creation of metal excess defect is called F center. Here F does not stand for female. Okay, it's called F center. F, this letter L, F is being taken from a German word. We call it Farben. Farben means color. You know why? After this metal excess defect, the sodium chloride, which is supposed to be colorless, pure sodium chloride, though you see white, actually it's not white, it's colorless. Okay, it's as transparent as glass. So it will look yellow. It will look yellow. Now, how to define F center? Okay, see here. Where the electron are there? Electrons are in those places where originally chloride was there. So F center is a phenomenon where the free electrons are occupying the anionic vacancies. So here the free electron is occupying the anionic vacancies. Here, so what I can write now? Acha, now please draw this one. Please draw. After that,
Done, sir.
okay. So have you written this one, F center? Son of the See, these are the anionic vacancies.
Done, sir.
I only hear your voice only. What about others are sleeping or what? Or they have already told you that you only tell. So Gitanjali, you only tell. You are Gitanjali, na?
No, sir.
Hmm?
No, sir.
What is your name?
Ishita.
Gitanjali, sleeping or what?
No,
Hello?
sir.
Miss ঘুমাচ্ছিস?
না, স্যার।
আমার মনে হচ্ছে। So I told you in this case, what do you find? The sodium chloride crystals now appear yellow. Okay. So what will write now here? Due to absenta the sodium chloride crystal looks yellow. We should know why it is yellow. See, I had already told you several times that any color is due to electronic excitations. See here, the electrons are free. When the electrons are free, it is very easy to excite. See, when you stay at home, you are under the surveillance of your mother, father. By chance, if your grandmother, elder sister, brother, then the politics. So anything you do, then you will get scolded. But when you go to school, when you go outside, nobody is there to say you don't do. Okay? Then you act by your own will. See here, when the electrons are within the atom, they are being controlled by nucleus, protons. Because of attraction, they cannot go anywhere. But these electrons are totally free. So, moment the visible light falls on them, immediately they get excited to the higher energy level. And later on they come back. And that imparts color to the crystal. So what to do right now here? With this question comes. Why F center makes the crystal colored? What will write now? The presence of free electrons in the anionic vacancies in the crystal lattice. Wait, I'll change the language. Just I'll change the language. Yeah. The free electrons present in the anionic vacancies in the crystal lattice undergo electronic excitation by absorbing electromagnetic radiation from visible light. A clear color. No, will not write. This language is wrong. Render color Sometimes this question also come. If they ask you why sodium chloride crystal is so yellow color, you will try this one. Why commercial sodium chloride salt appear slightly yellow color? So answer will be is due to epicenter. Okay. Then after that, sodium chloride salt have epicenter. Okay. Then after that, please write the same sentence here. Right, I'm not going to write. You write.
Done, sir.
Okay. Now let's see what will be the color, because alkali metal chlorides they show epicenter. Okay. Similarly, alkali metal chloride show a center. Okay. Then we'll write the salt and the color. Salt. Sodium chloride. Yeah. NaC. Lithium chloride. Pink. Potassium chloride ACL. Purple. Please don't forget. Okay. Now, consequences of F-center phenomena. What will be this? First, I told you it imparts color. Color. The crystal. Already you know. Sodium chloride. Yellow. Potassium chloride. You can say purple or violet, whatever you like. Okay. And lithium chloride. See, we have learned in our atomic structure, if any species contains unpaired electron, they are immediately being attracted by a magnet from outside. And this phenomenon is known as paramagnetism. So, do they not have unpaired electron? These electrons are remaining in the anionic vacancies. So, they are unpaired. What should I write now here? It renders paramagnetic behavior of the that is due to the presence of this. If the question comes, why F center develops paramagnetic behavior, you simply write one sentence: due to the presence of unpaired electron in their anionic vacancies. Okay. Third, free electrons are there. These free electrons can move. Okay. It helps the crystal to conduct electricity and placed between electrical field. Means what? shows semiconductivity.
Done, sir.
Now, this is in this example, what did you find? We created metal excess defect by addition of metal cation from outside. So metal cation we did not add. We added metal. That metal has lost the electron. The electron has gone inside to maintain the electrical neutrality of the salt, because we have seen in our diagram 2 sodium ion was extra. So that will make the crystal electrically charged. But each sodium has given 2 electrons. See, charge of the chloride is -1, charge of the electron is also -1. So 2 sodium ion charge is being neutralized by 2 electrons. So they are electrically neutral. So how did you make this crystal impure or defect? By adding the cation from outside. So this is our technique to make it. In second category, what I'll do? In second category, I will not add the cation. I will remove some anion from the crystal. See, solid anion we cannot remove, because ions are not visible to us. We cannot pluck and throw it. So we'll make a technique by which the substance will go in the form of gases. Okay, see. So I'm taking now zinc oxide crystal. What is the valency of zinc? What is the valency of zinc? What happened?
Sir, 2.
Okay. And what is the charge on oxide?
2.
Charge on oxide is not 2, -2. So this is our zinc oxide crystal. Okay. This is zinc oxide crystal is white. I have heated it. See, I think most of the girls who have visited the jeweler shop, any of the girl who did not visit jeweler shop, there are so many girl students are there. Any of the lady who did not visit the jeweler shop. In jeweler shop, you have seen, no, how they hit this gold and silver ornament. They have a blowpipe, na? So fire will come with the help of blowpipe. They'll direct the fire to the metal. So similarly, we can take it in a spatula, and we can heat it. Why? After heating, sometimes we'll find it very strange that solid mass has not melted, but it has become yellow. Take it out from the fire, keep it sometime outside and cool it, again it will become white. You know why? What has happened? When we've heated it, see here, O2 minus. Oxygen has how many electrons? Outermost shell, it has 2 electrons. Oxygen is atomic number is 8. So its formula is, electronic configuration is 2, 6. First shell contains 2 electrons, second shell contains 6 electrons. It is too short of oxygen. Okay? Because of that, oxygen combines with another oxygen to make it 8. This is our O2 molecule. Okay. And what is oxide? Why did I put 2 minus? These are the original 6 electrons of oxygen. So it has taken 2 electrons from outside. So this is equal to O. When I hit this oxide, O2 minus, here it becomes oxygen, and 2 electrons over. Okay, goes out. Now this, because we know oxygen atom is not stable, so 2 oxygen will combine to give you O. So this oxygen will escape from the crystal lattice in the form of oxygen gas. But when it goes out in the form of gas, it does not take these 2 electrons. It leaves the electron in the crystal lattice. Mind it, situation is very, very unusual. You are heating it. So when you heat it, what happens now? You'll find that this cation will move from this place. Why? Because of thermal vibrations. Okay. Remember your childhood. When you have done some ulta pulta at home, you got a soft step from your mother and father. Did you remain sitting there only? Huh? Hello. Huh? After getting one step from your father or mother, still you sit in your own place, or do not stand up and move away from that place? See, yeah, same thing. So when you have heated it, oxygen has left. All right, oxygen has left, and in this case, what has happened? The electron, it leaves the electron here, and electron also moved from his own place. Zinc also moved from own place, and they occupy the interstitial site. Clear? See here, what has happened? In this case, none of the zinc has gone out, but the oxygen has gone. So in this way, metal has again become excess. So this is also another example of metal excess defect. Second, why it is colored? Because of the presence of the electron, free electron in that interstitial spaces. All right. So, but if you cool it, then what happens? Again, it becomes colorless. No problem. Why? Because of the oxygen from the atmosphere again goes inside the crystal, pick up these two electrons, go to these own place. Okay, I remember still my childhood. Suppose if I say I come and find my father is very angry, and in that case, generally I have to go and stand outside the main gate. When everything becomes full, again I come back. So same thing here. When you remove the heat, oxygen from outside will come, pick up the two electron, go to its own place. Zinc also will come to its own place. So this is also another way of creating metal excess defect. Understood? But what is the difference between the absenta? In case of absenta, we find electrons are occupy the anionic vacancy. Exactly the place where chloride was there, it goes there. But in case of the heating of zinc oxide, we find because of thermal vibrations, the electron as well as the zinc moves from their own place and occupy the interstitial space. So this is another one. I shall try to send you the note or you read from your.
Done, sir.
Now we go for metal deficiency. See, there are some compounds which is very difficult to get in the pure state or in the right proportions. These compounds are very few. But why does it happen like this? It happens because sometimes some of the cation go missing from the crystal. But if the cation go missing from the crystal, then these cations will be, crystal will be charged. But by any type of defect, the crystal may suffer. Salts will be always electrically neutral. So if one or two cations goes missing, how these charges will be compensated? So this can be compensated by changing the oxidation state of the metal. Or sometimes happens, some of the extra anion goes inside the crystal and occupies those interstitial spaces. If the extra anion goes to the interstitial spaces, then the crystal will have more negative charges. Again, those metal will change their valency to neutralize it. So you'll find many a time you find suddenly you have a guest in your house. Then your mother never says that, sorry, we have cooked only for my family, so I cannot provide any food to you. what she will do? She will reduce a little bit from everyone and try to feed that guest. Same thing happens here also. So these are so natural, you know everything. Only thing is that it is being written in black and white in your chemistry textbook. So let us take the example of ferrous oxide. Okay. So it is Fe2 plus O2 minus. Fe2 plus O2 minus. Fe2 plus O2 minus. Fe2 plus very sad. Matara শেষে negative and positive will not be. See, this should be the ideal crystal. Number of the ferrous ion, these are called ferrous ion, and number of the oxide ion should be 6. But we find maybe one of this goes missing. One of this, if one of this goes missing, what will happen? See here, crystal will develop. For each ferrous ion, there will be 2 extra negative charges. Then how to neutralize these extra negative 2 negative charges? You know what will happen? The nearby iron Fe2 plus is there now. You will find it will change from Fe2 plus to Fe3 plus. See, plus 1 extra, and this will be plus 1 extra. Charge is neutralized. But if you find if you calculate, you'll find the iron is less. So these are called metal deficiency defect. Generally, these metal deficiency defect are being shown by ferrous oxide, ferrous oxide, nickel oxide.
Done, sir.
Okay. So let us see. So what is the normal formula of ferrous oxide? Normal formula of ferrous oxide. I will not write that. I'll write stoichiometric. is what? Fe and O. There. For time being, you write here 1.00, 1. 1:1. But the available ferrous oxide show a range of Fe 0.93 to Fe 0.96. See, is this stoichiometric ratio? Stoichiometric ratio should be a whole number. See, is it whole number? It is not whole. Okay? We'll do a numerical. Okay? This numerical is not done in your book. So let us try to do for our entrance exam. So let me write here. Ferrous oxide on analysis show an empirical formula of Fe 0.96 O1. Okay. Calculate the percentage of Fe2 plus and Fe3 plus ions. Don't faint when this type of problem is given. It's very easy. Write down. Then after that, I will show you. Finish writing. Now let us try to understand. Then you'll write. You'll write here. Let the number of Fe2 plus ion is equal to X. Okay. Therefore, the number of Fe3 plus ion see what is the total number? 0.96. it will be what? 0.96 minus x. All right. You don't write. You just try to understand. Don't write. Now see. Even if it is having defect, metal is less, but the charge is 0. So in that case, if I add the positive charges and the negative charges, total charge should be 0. What should I write now? Yes, the crystal is electrically neutral. So the total number of positive and negative charges should be same. So I'll write now. What is the charge of this? +2. So what we can write now is x into +2 plus 0.96 minus x into what is the charge? +3. Now I have to add here the negative charges of oxygen. How many oxygens are there? 1. So right now here plus 1, 0.00. What is the charge? -2. We know oxide is -2 is equal to 0. That is 2x plus I'll multiply this one. X. So what do you find? Therefore, x is equal to 0.8. Okay. So now what I can write? Therefore, number of Fe2 plus ion is equal to what? 0.88. The number of Fe3 plus ion is equal to 0.96 minus 0.88. So it comes to 0.08. So what is the percentage now? Therefore, percentage of Fe2 plus ion is equal to 0.88 by 0.96 into 100. So it comes to 91.66. And percentage of Fe3 plus iron 100 minus 91.66 is equal to 8.3. So this is not difficult.